Good morning, everyone. I want to welcome all of you to the James Mahoney Memorial Lecture. And as people are entering into the platform, I thought I might just take a couple of minutes to tell a story about Jim Mahoney and a little bit, give you a little bit of a sense of why this lectureship exists. I became executive director of AMS in 2004. And at that time, I reached out to Jim because he was a past president of the AMS. He had led a major strategic planning process, and I thought he might be able to give me some advice and some thoughts in terms of where I might want to set my priorities. He was the deputy administrator for NOAA at that time, and so when I reached out to him, I said, you know, would it be possible in your busy schedule to give me just a couple of minutes in a phone call so that you can provide a little bit of input to me as I start this new position. Instead, he came back and pretty much ordered me to make the trip from Boston down to Washington and spend some time with him. I did that, and he had blocked off a significant amount of his schedule over the course of a day that we were able to get together. And we sat in his office and we talked about just a wide array of things having to do with AMS, how I could be most effective in this new position that I was entering, the things that I might want to think about as I'm progressing through that. It was an incredibly generous offer from him to do that. He gave me wonderful advice that I continue to use as I work through this terrific position here at AMS. And it left me with this feeling of kind of just what a special person Jim is and how much he gave to all of us within the community. And that's one of the reasons, and perhaps an important reason, why both NOAA and AMS are so proud to sponsor this annual lectureship in honor of Jim. And really why this lectureship exists is because of the kind of person he is, the kind of impact that he had on so many of us, as well as the community itself and the profession. So with that, let me just say that it's my pleasure to have the opportunity to introduce this year's speaker. This is the 6th Mahoney lectureship that we've done. And it's wonderful to have our current speaker today, Margaret Leinen. Dr. Leinen is the director of the Scripps Institution of Oceanography. She has been since 2013. She also serves as the Vice Chancellor for Marine Science at the University of California at San Diego. I would encourage you to take a couple of minutes and read her full bio. It's extremely impressive. I'm going to do an incredibly inadequate job of summarizing that by just saying that she's very well known for her work in ocean biogeochemistry and paleoceanography, and for her leadership in issues of climate change and sustainability, both within the US and also internationally. The title of Dr. Leinen's talk this morning is The Ocean, Weather, Climate Nexus. We do expect to have some time for questions at the end of this talk, so if you have some thoughts or have some questions, please don't hesitate to put those into the chat as the lecture goes on, and we'll try to get to those when we get to the end of Dr. Leinen's talk. So with that, Dr. Leinen, let me turn the floor over to you.
Thank you so much, Keith. It's a pleasure and an honor to be the 2021 James Mahoney Lecturer for the AMS meeting. Next slide. So I too had the same picture of Jim, and I wanted to tell you a little story about my work with Jim when I was in Washington, DC, to give you some sense of why it's such an honor for me to give this talk. In 2000, I went to Washington to be the assistant director of the National Science Foundation for Geoscience. And in that position, I became chair of the then US Global Change Research Program, which was the interagency program to coordinate and to prioritize US research in global change. And that was also an election year. And during that year, George Bush and Al Gore were the candidates for president and were talking about climate change on the national stage, with Al Gore really emphasizing the need for action on climate change. At the end of the year, of course, Bush was elected. And after the inauguration, we began planning for our interactions with the Bush administration. We didn't hear too much from the administration until after the director of the Office of Science and Technology Policy was appointed, Jack Marburger. And he scheduled a meeting with the committee in the late spring after a cabinet process that the president put in place to look into the topic of whether climate was changing and whether humans were having an impact on that. And it was a very interesting process with a lot of stakeholders meeting with the cabinet from the science community, the policy community, the various groups like transportation, energy, and so forth. And at the end of that process, the administration said that they still had serious concerns about whether climate was changing and whether humans were having an impact on that. Later very late in the spring, the director of the Office of Science and Technology Policy asked to meet with the US Global Change Research Program members. And he came to tell us that we would no longer have an apolitical head of that committee, whether from NSF or any other group, and that there would be a political appointee who was put in charge of the committee. And of course, the committee made up of agency scientists who were working on global change was very concerned about this. But it wasn't until much later in the year that we understood that it would be the new deputy administrator of NOAA. But when we heard that that appointee was Jim Mahoney, everyone sighed a huge sigh of relief because we knew Jim. We knew him from his work on the acid rain assessment. We knew his work from his own science, faculty member at Harvard. We knew him as a former president of AMS. And when he came to work with us, it was also clear that his very strong commitment to science and to ethics, his strong ethical position, were going to make sure that the program continued. It was renamed the Climate Change Science Program, and I was proud to serve as a vice chair of the committee together with Ari Petrinos from Department of Energy. The many questions that the administration had were also coming up in respect to the fact that the committee was supposed to develop the second national climate assessment, which was mandated by Congress, but which the administration really didn't want to see move forward. And Jim, I think the only person that could have led us through that time was Jim Mahoney, who as a political appointee was able to interact with the highest levels of government, and who as an incredible scientist could lead us in the effort to try to work our way through that. And working together, he led us in developing a strategy of putting together a set of 21 synthesis and policy assessments, each of which was pointed at a question that was being asked of the community. The first one of those was pointed at the question of the divergence in the long-term record of the lower troposphere and upper troposphere temperatures, which was being used as by skeptics as reason for saying that we didn't know whether climate was changing. And that assessment, all of the assessments were peer-reviewed, and that assessment not only showed the validity of the data, but also showed that both theoretically and in models, that divergence of temperature in the troposphere was expected and was consistent with climate change. So this individual, this amazing scientist and amazing strategist led us through one of the most perilous times for when things could have gone very wrong with the relationship between the science agencies and what had been the U.S. Global Change Research Program and the administration. And in fact, led us to become a very trusted committee of the U.S. Of the government, and a committee which was able to do its work in concert with the Bush administration. Jim had my complete support. He had my highest admiration for the job that he did in that very, very difficult role. And I think that it's one of the reasons that so many have wanted to have this lecture. I should mention that at the time that I was chairing the U.S. Global Change Research Program, a former Mahoney lecturer, Richard Moss, was the executive director of the program, and that he also shared this incredible respect and admiration for Jim. So next slide. One of the things that we didn't talk very much about at that time was the relationship between the ocean and climate, no less the ocean and weather. But I think that over the last 2 decades, it's really emerged as a major influence in climate change and really a very, very important component to be considered as we think about weather and weather prediction as well. Next slide. So I'd like to look first at one of the iconic components of the system that we think about when we do think about weather, climate, and the ocean, and that's El Nino. Next slide. Between 2011 and 2017, the state of California was in a historic drought, an exceptional drought. It hadn't been as deep a drought since for 1,200 years. And it culminated in July of that year with almost 60% of the state in exceptional drought. Really a very, very difficult time for the state. Next slide. So early in 2015, as we stayed in this drought, the signals for both the NIÑO index and the ENSO index suggested that a very strong El Nino was coming. And El Niños in California are associated with a lot of rain. So the state really prepared to face not only a lot of rain, but also perhaps an end to this millennial drought. And the purple curve there is from the 1982 El Nino, and the very dark green is from the 1997 El Nino, both of which brought terrific rain to the state. Next slide. In fact, the signals were so strong that Bill Patzert, an El Nino expert at JPL, said that this was going to be a Godzilla El Nino. And of course, that was taken up by the weather community. It provided a lot of opportunities to talk to the public about El Ninos and their impact. And this image from a California CBS station used the imagery of Godzilla with the force pointed straight at California and Baja California. So we were really prepared for a tremendous amount of rain. The water reservoir managers were planning their strategies for when they would release water from reservoirs in advance of the rainy season so that they wouldn't be faced with the idea of the reservoirs being overcome by the water and having to release water at the same time it was raining. The agricultural community was planning what they would do in terms of their planting, in terms of their management of agricultural lands in the face of all this rain. Next slide. So it did, in all respects related to the indicators of El Nino, turn into a historic El Nino. And in many parts of the world, that El Nino was incredible in terms of its impact. Next slide. But in terms of California and rain, no such luck for the state. On the left side of this panel, I'm giving you an example from San Diego, but the entire state was very similar. On the left side, the graph shows the percentage of normal precipitation occurring during each month of the rainy season. And this is for all of the data that we have right up through this year. And so you can see that as we enter the rainy season, more and more of the percentage of total precipitation, average total precipitation, comes in that month. And so at the light blue colors at the top represent very, very strong precipitation, and those are primarily the very big El Nino years. At the bottom, La Nina, and then most of the records are in that dark blue section that show, in fact, 2/3 of the records are in that section, which show how much precipitation is coming on average. And I'll come back to why 2020 is illuminated. On the right-hand side, you can see the records for the primary El Ninos of the last 50 years. And 1982 is right up at the top with about 180% of normal precipitation coming by the end of April. Total for the 82-83 El Nino was 200% of normal precip. 1997, the same, with very high rainfall and in total about 160% of normal rainfall. And then you see 2015 down there. And I've highlighted 2020 because this is the 2020 was an El Nino year, although it was a very weak El Nino. So you can see that 2015 was more like a normal year, no real significant precipitation at all. Next slide. At the same time, a very unusual sea surface temperature anomaly had developed in the Northeast Pacific. And here's the anomaly with temperatures of up to 2 degrees warmer than average in the Northeast Pacific in early February. Next slide. And by the beginning of the rainy season, this is also sea surface temperature anomaly, that anomaly had developed multiple lobes in the Bering Sea, the Gulf of Alaska, and off California and Baja. Next slide. And that sea surface temperature anomaly actually extended throughout 2015 and into the next year. Next slide. And because of its size, its persistence, Nicholas Bond from University of Washington described it as the blob, like the blob from the horror movie. Next slide. And this became a meme for both scientists and the public. And this cartoonist featured El Nino versus the blob, fighting it out in California for weather impacts. Next slide. And by the end of the year, scientists were saying that the blob had won over El Nino. And that was certainly true for ecosystem impacts, tremendous ecosystem impacts in the Northeast Pacific with the blob and historic temperatures really devastating many ecosystems. We had tropical species occurring all the way up into the Chukchi Sea. Next slide. For precipitation, however, I should have said at the time, many were saying that it was the sea surface temperature anomalies that were the result of low rainfall in California, and that they were steering weather systems to the north so that northern Oregon and Washington were indeed having the sort of rainfall that we usually have in California during El Niños. However, subsequent analysis showed that the difference in California rainfall, shown here in terms of the precipitation anomaly for the 82, 97, and 2015 El Niños, is really related to sea surface temperature anomaly patterns in the Indo-Pacific region. So just a very interesting situation where the sea surface temperature off California was initially identified as the reason for low rainfall, but that subsequent reanalysis showed us that it was the ocean far from California in the Indo-Pacific area that set up this, situation where a very strong El Nino would have almost no weather impact in California. Next slide. So that was the 2015-16 El Nino. And 2019, we again saw incredible temperatures offshore in the Northeast Pacific. And this video shows the January to September sea surface temperature anomaly in the Northeast Pacific. And you could see it developing there. It was, although the duration of the 2019 heat wave was not as long as the 2014, 15, 16 heat wave, its intensity was greater. And the Scripps Pier has been recording sea surface temperatures for 104 years. And the 2019 August 7th temperature was 79.2 degrees Fahrenheit, well above the average for our area, which would be 68 degrees at that time of year. So we were seeing record temperatures. And this idea of record temperature and marine heat waves really started, or the idea of marine heat waves really started in the early 2000s. And we began to look at those and their relationship to climate and their relationship to weather. Next slide. So this work examined 7 of the largest marine heat waves between 1981 and 2017. And the little maps show all 7 of those heat wave areas, the Northeast Pacific being the largest of them. And the upper, both the time series on the left from 1981 to 2017 and the map at the top show the duration of marine heat waves, and the red ones are those 7 major heat waves. The middle panel shows the peak temperature in the heat wave, and the lower shows the intensity with the temperature, the duration, and the extent of the heat wave. And as you can see in the time series, for all 3 of those parameters, there has been a big increase in duration, peak temperature, and intensity for heat waves in the Pacific, and not only in the Pacific, but worldwide. Next slide. Amaya and colleagues looked at the relationship between physical features in the physics of the Pacific and these heat waves and their increase, and found a very strong relationship between the sea surface temperature during the heat waves and the mixed layer depth in the ocean. And on the right, the red line shows the actual temperatures as measured by 3 different measurement systems, including Argo. And the blue and black lines show the model results for coupled ocean atmosphere models that include both mixed layer depth and sea surface temperature. And the model results extend out to the end of the century and show that there's a very high likelihood that mixed layer depth will continue to be diminished through the end of the century. So what we've experienced already suggests a shoaling of almost 4 meters in the mixed layer depth. Average mixed layer depth is about 80 meters in this area, with more shoaling to come of almost another 4 meters. So as much as we've already experienced almost a 5% decrease in average mixed layer depth in the Pacific since the time that we've had very extensive measurement systems, and could experience more. So this has led those who work on marine heat waves to suggest that marine heat waves will continue to increase and be an important factor in affecting not only ecosystems, but also the weather systems in the Pacific. Next slide. So all of those relationships between marine heat waves and El Nino were based on sea surface temperature, and our ability to look at those with great detail has really depended on the development of the Argo system, which I'll talk about later, for being able to have much more information and much more data to use to look at the relationship between the ocean and El Nino and the advent of marine heat waves. But sea surface temperature is just one indicator, and ocean heat is another one, and an important one. The top, and I think it's worth remembering that the top 3 meters of the ocean can hold as much heat as the entire atmosphere. So it's a really potent driver of climate and weather. Next slide. And I'm not going to go into great detail, But the relationship between sea surface temperature and ocean heat and hurricanes is one that has really been the focus of a lot of research. And AMS has had several important keynote speeches over the last 20 years on hurricanes and the potential for hurricanes to change in frequency or intensity as a result of climate change. GFDL maintains a portion of its site on global warming and hurricanes, on which it reviews not only its own research, but the research of the entire community. And the latest update of that discusses the relationship between hurricanes, sea surface temperature in detail. And based on GFDL results, as well as those of other modeling groups, they conclude that a future increase in tropical cyclone precipitation rates is likely. And there's a reason that they're using the term tropical cyclone instead of hurricane, because the results appear to be somewhat different between the Atlantic basin and the Pacific. But for cyclones in general, a future increase in precipitation rates is likely with increasing sea surface temperatures. An increase in tropical cyclone intensity is likely, and an increase in very intense tropical cyclones is more likely than not. And then a medium confidence in decrease in the frequency of weaker tropical cyclones. So all of those relationships are with sea surface temperature. Next slide. But the community is starting to look at ocean heat content rather than just sea surface temperature. And this panel looks at the sea surface temperature and the ocean heat content of the Western Atlantic and the Gulf of Mexico. And superimposed on that is the track of Hurricane Katrina. And the little colored dots on the hurricane track indicate the intensity of that hurricane from a tropical depression to a Category 5 before it hit Louisiana. And the authors argue that the sea surface temperature certainly can influence the hurricane, but a more accurate predictor of the intensity of hurricanes is the ocean heat content of the waters that they're moving over. So they show the intensification of Hurricane Katrina as it moved over that area of much larger ocean heat content in the middle of the Gulf during its path, and that its intensification could be related to ocean heat content rather than sea surface temperature. So this is a very active area of research looking at the relationship between sea surface temperature and ocean heat content. But we hadn't been able to have the kind of record of ocean heat content that's shown here for the 2011 study and for Hurricane Katrina until recently. We had sea surface temperature from satellites, but we didn't have very complete records of ocean heat content. Next slide. Much more work is being focused now on ocean heat content because we know that 93% of the heat related to climate change and warming is in the ocean rather than in the atmosphere. And this is the record of global ocean heat content change in the upper 2,000 meters based on Argo for the last 15 or so years, and shipboard records and moorings for the earlier time. And it just shows this dramatic increase in the heat content of the ocean, with the error bars decreasing regularly and being very small now that we are using Argo. So a very interesting area of research for tropical cyclones, for hurricanes, and looking not just at sea surface temperature, but ocean heat content as well. Next slide. The next component of the climate and weather system that I'd like to look at is atmospheric rivers. And this wonderful image is a satellite imagery of the integrated water vapor content of the atmosphere from NASA. And the brighter colors are higher integrated water vapor. And obviously, the tropics have the highest water vapor contents because of temperature and evaporation. But I'd like to call your attention to those thin tendrils coming off of the equatorial region and going into the temperate region. And those bands, those thin areas of much higher integrated water vapor are what we call atmospheric rivers. So they're like rivers of water vapor coming off of the tropics and extending up into temperate zones. And these are, in spite of the fact that they look much lower in atmospheric and integrated water vapor than the tropics, and they hold a tremendous amount of water. So an individual atmospheric river holds as much water as 25 Mississippi rivers. So that's an incredible amount of water vapor moving from the tropics into the temperate region and encountering land when as it comes up to continents. Next slide. So atmospheric rivers really became prominent in the popular media in 2017 when a very intense atmospheric river system hit California, creating an incredible flooding in Northern California. And this picture of Lauren Doloman in Gurneyville, California, with her kayak in her home, was the front page of the San Francisco Chronicle, got picked up by the New York Times, the Washington Post, and weather media across the country, and really highlighted the potential of these storms to cause as much damage as hurricanes do. Next slide. One of the, at Scripps Oceanography, we have a very active group, the Center for Western Weather and Water Extremes, that studies all aspects of atmospheric rivers. And one of the things that we found is that although the atmospheric rivers have the water vapor to create incredible precipitation, the sea surface temperature near the coast makes a very big difference in how much rain an atmospheric river actually brings. So the difference between its potential and the actual precipitation is strongly dependent on sea surface temperature. Next slide. Recently, we have been able to categorize atmospheric rivers in the same way that hurricanes and tornadoes have a scale for them. And the atmospheric river category scale really emphasizes that, well, for example, in California, more than 50% of our annual rainfall comes in atmospheric rivers, and a very few atmospheric rivers, 4 or 5 events during a year can bring half of our rainfall during the year. So the scale emphasizes that at the lower levels that atmospheric rivers are primarily beneficial and really bring the rainfall we need to the state. But at the upper levels, categories 4 and 5 are very hazardous, with category 5 primarily hazardous because of the intensity of the rainfall and the flooding. Next slide. So a couple ocean atmosphere models suggest that under warmer conditions, atmospheric rivers will be fewer in number, but will be longer, wider, carry more water, and produce more rainfall. So atmospheric rivers already have the potential to be hazardous, and under warming scenarios suggest that they have even greater potential for hazardous rainfall. Next slide. A very interesting perspective is that we think of atmospheric rivers now primarily in terms of their impact on temperate environments. And in the US, we look at them primarily in terms of their impact on the West Coast. But most water vapor transport to the poles occurs over ocean sectors, and about 60% of the water vapor transport in those regions is transported by atmospheric rivers. So many of these extend into polar regions, and they control more than 70% of the variance in water vapor transport above 70 degrees of latitude. Next slide. So water vapor, of course, in polar regions brings snowfall, but all of you meteorologists understand that that water vapor is also transporting heat to the poles in the form of latent heat released during rainfall or snowfall. So atmospheric rivers are projected to carry more water and therefore more heat to the poles in a warmer world. Next slide. And scientists are beginning to look at exactly how that is taking place. And here you see Sushil Adesimile's work on the tracks of atmospheric river storms to Antarctica and their impact on snowfall. So those atmospheric rivers are the ones, this is the Pacific sector of Antarctica. And you can see that there were changes of up to a centimeter a day in the height as a result of snowfall in Antarctica, coming virtually entirely from atmospheric rivers, bringing that snowfall to Antarctica. So the big question now is whether the balance between snowfall and heat, and therefore melting, which of those dominates now and into the future. Next slide. Oops, I thought there was another slide in there. So now the focus is on determining whether snowfall will exceed melting or melting will exceed snowfall associated with atmospheric rivers. The work that's been done to date suggests that the heat effect from atmospheric rivers is greater than that of snowfall, and that in essence the greater number of atmospheric rivers anticipated in the face of climate change will add to the temperature in creating melting and in destabilizing ice sheets in Antarctica. So most of the relationships that I've shown you between the ocean and weather effects, interannual variability like the El Nino, and the projections for climate have depended on the increase in our ocean observations with time. This kind of ability to analyze the impacts in detail and the ability to project into the future is really dependent on a very, very complete set of ocean observations. Next slide. One of my predecessors as a director of Scripps Oceanography, Roger Avell, said that great periods of oceanography are defined by new kinds of instrumentation. And that certainly applies to ocean science, but I think that it is already applying to the ability of oceanography to assist in understanding meteorology and climate change. Next slide. Some examples of that are the Global Drifter Array. This is an array of surface drifters. There are about 1,250 drifters on average at any given time, and they measure temperature and sea surface pressure. And these are essentially the only measures of sea surface of lower atmosphere pressure for most of the globe, since the ocean covers 70% of the globe. And as a result, they have the largest positive impact per observation of any data in forecasting, especially the long-range weather forecasting. So we're critically dependent on this set of ocean observations. And it's really only been in the last 20 years that we've had this data set and this amount of data coming for sea level atmospheric pressure for the ocean and for prediction. Next slide. I mentioned ocean heat content before, and this will give you some sense of how important that is. So we've known for some time that more than 90% of the heat resulting from fossil fuel emissions and warming goes into the ocean. And the last IPCC assessment, assessment 5 in 2013, used this image. And this was the state of our knowledge of ocean heat content at the time. But even this was able to show us that most of the heat resulting from fossil fuel emissions goes into the ocean, with the upper ocean containing most of that heat, the deep ocean in dark blue, ice in that thin gray line, the land in brown, and the atmosphere, that very small dark purple line. So for all of the impacts that we're seeing from warming in the atmosphere, they're nothing compared to what is happening in the ocean. And the ocean is really buffering us from much more substantial heat impacts. The dotted lines show the uncertainty in that measurement. And as you can see, that uncertainty was very great in the record extends from 1970 to 2013. The record was very great at the beginning because we were dependent on measurements at sea and heat content measurements from cruises. During the time of the WOS program, we were able to increase the number of heat content measurements, and the error bars went down. And then with the advent of Argo, they have reduced even more substantially. But still, this was what we knew a decade ago. Next slide. Since then, the Argo float system has really changed our ability to view the ocean and to understand its physics, its dynamics, and its effect on weather and climate. So Argo floats are autonomous floats that operate for many years. And most of the time they're drifting at a depth of about 1,000 meters. And roughly once a week, about every 5 to 7 days, they sink to 2,000 meters and then rapidly ascend, making measurements of temperature, salinity, conductivity, and depth while they're ascending, and then send back all of the data via satellite when they come to the surface, descend again, and go through the same cycle. So with almost 4,000 floats in the ocean, about every 5 to 7 days, we're getting 4,000 measurements of the upper 2,000 meters of the ocean for temperature, salinity, and depth. And this has allowed us to look at the ocean with orders of magnitude more fidelity, and our time series understanding is so much greater than it was before Argo started in the early 2000s. Next slide. So this graphic shows the ocean heat content in ocean depth regions between 1993 and 2000. So each of the red lines is from the Argo floats and looks at an individual depth region. The blue and green lines are for individual depth regions below 2,300 meters. So those are primarily still from ocean cruises, but a new program, Deep Argo, has developed technology that will allow Argo floats to do full ocean depth measurements. And there are only about 50 Deep Argo floats at present, but the plan as part of the Argo program is to build out that system so that we will have as much understanding of the deep ocean as we do of the ocean above 2,000 meters. But even with the data that is there, that we currently have from Deep Argo deployments and from cruises, you can see that whether it's the upper ocean above 2,000 meters, the lower ocean, or even the deepest depths of the ocean below 6,500 meters, all three areas are increasing in temperature. Next slide. And this graphic shows the upper 700 meters from Argo data between 1993 and 2019. So in comparison with that slide that I showed you from the fifth assessment, we now understand in much more detail what's happening with ocean heat content. And we can see that that areas in the Western North Pacific, the Western North Atlantic, the Arctic, and the Southern Ocean are the sites that where the upper ocean above 700 meters is warming extensively with up to 6 watts per meter squared of increase in ocean heat content. And that some areas, especially where deep water is being formed, are actually cooling. But this has completely changed our ability to include the ocean in our thinking about the total ocean atmosphere system and the heating that's occurring as a result of global change. Next slide. And here is the record for the full 2,000 meters that are covered by Argo. And as you can see, although the heating is greatest in the upper ocean, and this is I should point out, this is relative to the year 2013. So the earlier part of the record is not cooling, it's just cooler than 2013. But we see the warming of the entire upper 2,000 meters of the ocean during this time. And that's why we feel so confident in those measurements of total heat transfer and the idea that the ocean is taking up 93% of the heat. Next slide. In 2017, the UN General Assembly passed a resolution establishing this decade, 2021 to 2030, of the UN Decade of Ocean Science for Sustainable Development. Next slide. And their catchphrase is the science we need for the ocean we want, primarily because many of the big challenges for the UN Ocean Decade are focused on issues related to ecosystem and pollution in the ocean. Next slide. But several of those challenges are extremely important for us for climate and weather. And one of them is to enhance our understanding of the ocean climate nexus and build resilience to the effects of climate change. A second, to enhance multi-hazard early warning services and mainstream community preparedness and resilience. So here, the meteorological community and especially the forecast community are very much a part of the thinking of the UN Ocean Decade, with being able to develop much stronger early warning services for any hazards that are related, any weather hazards that are related to the ocean. And then finally, to ensure a sustainable ocean observing system across all ocean basins that delivers accessible, timely, and that should be an actionable information. So even the Ocean Decade is focused on this nexus of climate, weather, and the ocean, and intends over the decade to invest much more in enhancing our ability to make measurements in the ocean and to use those measurements to understand climate change and to understand the relationship between the ocean and weather. Next slide. Oops. This is just highlighting that challenge for a sustainable ocean observing system. Next slide. In 2000, around that same time, the UNFCCC Conference of the Parties asked that the IPCC develop a special report on the ocean and cryosphere in a changing climate. Next slide. And that report was delivered in 2019, just ahead of the Madrid Conference of the Parties, COP25, which was focused on the relationship between the ocean and climate for the first time. And this COP really brought home the message that the climate is intimately tied to the ocean and intimately tied to, and our ability to understand climate change and to deal with it is intimately tied to our understanding of the ocean. Next slide. So over this last decade, over the last 20 years especially, we've understood that Earth systems all work together and that we cannot ignore the ocean as we look at both the weather and climate. And so the message is that we need to invest in those ocean observing systems and invest in understanding the relationship between the ocean and climate and between the ocean and weather. Thank you very much.